The theory and the process of how does this work? You can remember dry ice. Just remember the acronym ICE. There is an impact. It is very cold, and there is an expansion when it sublimates. Just remember ICE. There is some kinetic energy. Dry ice has very little hardness, so in order to get any work out of it, you got to get it accelerated pretty quick. If you notice on the chart, this is the Mohs scale of natural substances known to man, talc being the softest, a diamond the hardest. Dry ice is right up there with the soft side. So to get work out of it, you've got to get it moving at about 600 to 1,000 feet per second. That will bring some kinetic energy. Kinetic energy being measured, 1/2 the mass times velocity squared. Good to keep that in the back of your mind. You do have the ability when you take dry ice and you apply this process to your manufacturing of medical devices to control the amount of kinetic energy that you bring to the process. On an ambient substrate, this is probably doing 60, maybe 65% of your cleaning. So this is where you're going to get the biggest bang for your buck, where you make your adjustments in your velocity controls on pressure to control the kinetic energy and your particle size. Even if you choose to use a 3 millimeter, you're able to knock that down with splitters, or sometimes called fragmentation. You can knock down that particle size with some pins inside the nozzles that allow you to reduce the kinetic energy. Helpful when you get on a substrate that may be gentler. It is also very cold. There is a thermal effect to this. Dry ice, as we talked about before, for us in Fahrenheit, it's minus 109 degrees. It's the coefficient of thermal expansion and contraction of dissimilar materials. The contaminant is not the same as the tool steel or the mold base, the H13, the P20, whatever the mold's made out of. That dry ice will impact the contaminant. It will cause that contaminant to embrittle. It'll cause it to freeze, and it'll lose its bond strength. It'll lose its adhesion because it just got instantly frozen, and it just frees it up from the substrate. So you have cracked that contaminant with a little bit of kinetic energy. You freeze it, and then it lets loose. The higher the delta T that you get between the contaminant and the dry ice, which means the hotter the tool, the hotter the mold, the more the cold contributes. Got some test studies that show at 500 degrees C, which I don't think any of us are going to get there. Even if you're molding rubber, you might get into the low 200s. But the higher that delta T, the more this effect contributes to the clean. 500 degrees C, it's been estimated and calculated to be 50% of the clean. So translate that. If you clean something that's hot, you don't let it cool down, it will clean easier, it will clean faster. And if you're wondering what's the magic in that, the magic is the thermal property, the thermal effect of the dry ice cleaning is contributing more on a substrate that's hot. The last effect that come into play after I've cracked the contaminant with some kinetic energy, I've embrittled it instantly with the cold. On impact, that solid CO2 will phase to a gas. It's going to volumetrically expand, depending on where you are sea level, about 800 times its size. So all these little micro explosions go on the surface, and they just blow the contaminant off of the whatever that substrate is you're cleaning. So it goes back into a gas, and it's dry, and thus the name dry ice. And that's the magic of it. The kinetic energy is common to some other blasting media, but that thermal property, this expansion properties are very unique to the magic of dry ice. The dry ice comes in kind of a diagram here. You hit the contaminant, it shrinks it, it's cracked it, and then it expands. Let me just give you a little quick video of what that would look like in a simulation. That is what dry ice cleaning looks like. The dry ice is accelerated at high velocities. It is impacting the contaminant. It's traversing. It is embrittling the contaminant. It is phasing back to a gas, and it is blowing the contaminant off. That is the entire process. If you can understand those three aspects of it, you can then begin to adapt. How much kinetic energy do I bring to the substrate I'm cleaning now? You're running a hot runner mold, you're cleaning the cavities, you can go at it with a lot of kinetic energy. You get to the top of the hot runner system junction box, terminal strips, wires, You're going to want to lower the kinetic energy so you don't strip the insulation off of the wires.